We'll take a little detour into physics here and talk about polarized light. Ordinary light has waves that vibrate in all possible planes perpendicular to its path. So here we have light going from point A to point B. And non-polarized ordinary light is going to have waves vibrating in the vertical and in the horizontal and in the diagonal and every possible plane that's perpendicular to this path. When we pass light through certain substances, it can cause all of the waves to vibrate in parallel planes. Basically, it's filtering out any of the waves that do not go in that one particular plane. And so when we look at this, this is like a filter here with vertical slits. And so only the light that's vibrating up and down can get through. And the other light is blocked. And when light comes through like this, now all of the waves are vibrating in this one plane. And we say that light is plane polarized. So all of it's vibrating in the one plane. We can measure the plane polarizing, the polarity of the light using a polarimeter. So what a polarimeter does is it has, you've got a source of unpolarized light, and then you run it through a polarizing prism, a polarizing filter, and I'll show you an example in just a minute. And then that comes through this sample tube, and then you've got another polarizing, it doesn't paralyze anything, polarizing prism here. And if we rotate this, we can get them to completely block the light. Have any of you ever had polarized sunglasses? Or at least played around with them at the store? If you're wearing polarized sunglasses, the television screen looks weird, your cell phone screen looks weird, your computer screen looks weird, because the light that's coming off those screens is polarized. And so with your polarized sunglasses, then it interacts in funny ways with the polarized light coming off of those screens. If you take two polarized sunglasses and turn them at right angles to each other, they will completely block the light. Let me show you how that works. So for the people watching on YouTube, there is a video of a guy messing around with some pieces from an LED screen, which does much the same thing that we just saw. So in the polarimeter, we're going to put a substance in here. Table sugar is optically active, and so you could put a sample into this tube, and it will rotate the light. We say that's an optically active substance. Because of the chirality of the molecule, it will twist the light a little bit. It will rotate it. So if you put a substance in here and it rotates the light, then instead of seeing complete darkness when you have these at right angles to each other, because it rotates it, you'll see a little bit of light coming through. And then you adjust the prism on this side so that it completely blocks the light again, because that's easier to see than when it's completely coming through. And so if this substance rotates light to the right, it's called dextrorotatory. And if it rotates to the left, it's called levorotatory. So this is left and right. To the right is positive, and if you think of a clock, the clock goes to the right. That's the positive, a clock going forward. And a clock going counterclockwise would be to the left, and that's the negative. And so that's how they measure the rotation of light. So a single molecule will rotate plane polarized light, just a little bit. The more molecules you have, the more rotation you'll get. But achiral molecules are optically inactive. they will not rotate the plane polarized light. Well, I take that back. A single molecule rotates the light, but in a sample of achiral molecules, you've got all these different conformations present, and so they're all going to rotate the light in slightly different ways, and the net effect is that they cancel each other out. If you have one enantiomer of a chiral molecule, all of those molecules are going to rotate the light in the same way, and so then the rotation adds up instead of canceling it out. So if we have only one enantiomer, there are no mirror image configurations. The rotation caused by one molecule does not get canceled out. If you have a 50-50 mixture, then it will not rotate the light because the effects of each enantiomer cancel out. So enantiomers, we've been talking about enantiomers. Those are mirror images that are not superimposable. They only differ in properties that are also chiral. They're going to have the same melting and boiling points, the same density, the same solubility. Anything in which they're interacting with something that is achiral, that does not have handedness, they are going to behave the same. Just like a baseball relates to a left-handed and a right-handed baseball player the same because it's achiral, it will interact with anything that way. If you have a right-handed glove and a left-handed glove, they're going to behave in the same way unless you interact with them in terms of a right or a left hand, and then there's a difference. But the other properties will be the same. The chirality of an object is most important when it interacts with something else that is chiral. So a left-handed baseball player is a chiral thing, or a person, left-handed. So when he interacts with a ball, does it really matter so much that he's left-handed? No, because the ball is not chiral. The bat is not chiral. Doesn't matter. He can swing it either direction. When he interacts with a baseball glove, now it matters because he wants to put it on his right hand so he can throw with his left. And a right-handed glove is not going to work for him. So what we find is that enantiomers rotate light in opposite directions, but by the same number of degrees. So they're mirror images of each other. One will rotate light to the right, one will rotate to the left, but they'll rotate it in the same amount. If we look at lactic acid, so here's lactic acid. Another way of positioning it is to look at it this way. This is the R version. If we look at this hydrogen going to the back, the OH here is going to be the highest priority, and then this one, the CO2, and then the CH3. And so we're going to look in order of priority. Let me write those down. So this is highest priority and next highest, and this is the third and this is the fourth. And so when we were determining the priority, I told you you can take your thumb and see how does it work out. If you point your thumb along this carbon-hydrogen axis, which hand works to start with the high priority and then move to the second and to the third. And so I'm getting a different result for that. These are going, oh wait, no I am not. This is coming out. I got my hashed wedges and my solid wedges backwards. The hydrogen here is coming out. So if I put my thumb out, and I use my left hand, I can't go from 1 to 2 pointing with my fingers. Here, carbon hydrogen's coming out, and I'm going from the OH to the CO2 around to the 3. Does that make any sense at all? Anybody? You're like, what are you doing? Reaching up to the screen and twisting your hands around. Anyway, this is the right-handed version, and that's the left-handed version. Right-handed version, left-handed version. If we look at their melting points, 53 degrees, 53 degrees. Their melting points are exactly the same. But if we look at the rotation of light, and alpha is the symbol that they use for that, this one rotates it to the left, 3.33 degrees, and this rotates to the right, 3.33. The degree of rotation is the same, it's just in the opposite direction. Now, this is really important. There is no obvious relationship between configuration, meaning R or S, and direction of rotation. That's why we had a different word for the plus and minus, dextrorotatory and levorotatory. And sometimes they're abbreviated D and L. Those are not at all related to R and S. Some R chiral molecules rotate light in the positive direction and some in the negative. And there doesn't appear to be any distinct relationship there. But what we do see is the two enantiomers, the mirror images, one rotates to the right and one to the left. And so when we're specifying that, we'll specify both the chirality and the rotation. So this one's negative. Enantiomers have important differences in terms of biological activity because many of the biochemical reactions involve another chiral molecule. If you have two chiral molecules interacting, then the chirality becomes very important. So lactic acid dehydrogenase is an enzyme that oxidizes lactic acid, but it only oxidizes the plus lactic acid. It does not oxidize the negative. Another example, the negative adrenaline, the one that rotates light to the left, is a cardiac stimulant. If you take the opposite, it doesn't do anything. It just has no effect on you at all. And so biochemically, stereochemistry is really, really important.